will do a brief introduction to find out who's in the room. Today, George Hugh is with us. He's going to speak to us about geothermal energy, which is very exciting. This is an AIA CEU course, thanks to the BSA's hard efforts. And I believe, I haven't seen the sheet, but I believe this will qualify for sustainable design as well as HSW, so you can get all your merit badges and stuff, which is great. We meet monthly, except during the summer, and except during months of Build Boston and residential Build Boston, because generally a lot of people in our group are very involved in those activities, and so we don't meet that time. Next month, just because sometimes it gets crazy at the end, we'll do the announcement for next month. We're going to have a presentation on cold-formed light steel joists. It's a big, long term, but basically it's a product that I ran into recently. That you've got your glue limbs, you've got your all these things. Now they're actually taking steel, rolling it, and it's very light gauge. It's like a giant, oversized stud is what it looks like. But it can do large spans, very rigid. It can be cut by carpenters, put on site, and is really a fabulous kind of no-brainer invention. It's got 65% recycled product, which is pretty amazing for a green product. It was developed, I think, in Australia. They've been using it for years. We're going to have that next month. So before we let George loose and school us all up, I'll start and we'll go clockwise.
Used to work for other engineering firms, BR+A and the AHA for a few years, and then I started my own firm and beginning of 2008. Do MEP stuff, especially HVAC, and also, as you can see, I do geothermal system design, also energy modeling. Okay, so today my topic is the geothermal HVAC systems, the basics, some application examples, and its benefits, and some issues that we may run into.
George, can you speak a little louder? So they're a little
okay.
Hard to hear you.
Sorry about that.
Thank you.
First, the geothermal basics. Here is a map which shows the geothermal energy across the United States. Blue colors in the map indicate you have groundwater with temperature less than 212 degrees. And the red colors underground water temperature above 212 degrees. As you can see, the geothermal energy is concentrated in the western part of the country. The eastern part in the middle, you don't have much. Like states in California, Nevada, Idaho, those states, they have a lot of high temperature underground energy available. First, we want to clarify two terms, the terminology, geothermal or GSHP, ground source heat pump system, okay? Now, according to DOE, Department of Energy, they classify the underground energy in terms of the underground water temperature. High temperature geothermal resources, where you have underground reservoirs of steam, hot water, and dry hot rocks. From those resources, you can design the electric generation systems with steam turbines. Okay, that's one of the examples. Moderate to low temperature geothermal resources. For those temperatures, I believe below 200 degrees, in that range, you use the heat directly for space heating. For that temperature, you cannot run a steamer engine to generate the electricity. So you use it directly for space heating. And then the lower temperature range, which means shallow ground geothermal resources, like for Boston area, New England area, across the country, basically everywhere. You utilize it with geothermal heat pumps. Now, according to USGBC, United States Green Building Council, for the on-site renewable energy, point purposes. Then two categories. First one, geothermal energy systems that use deep earth, water, or steam sources, but not with vapor compression systems for heat transfer. Those on-site energy is eligible for the lead on-site renewable energy point. Okay, and then the other category is geo exchange ground source heat pump, also called geothermal heat pump system. Those systems you use, you have a heat pump there. That is, you use the vapor compression cycle in order to get the underground heat. It's not eligible for on-site renewable energy credits, but because it's so efficient, it saves a lot of energy for the buildings. It's eligible for the energy and atmospheric credit #1 points. Okay. This picture shows a typical water-to-air geothermal heat pump. You have a casing, and then inside the casing you have 4 basic components: a compressor, evaporator, a condenser, and expansion valve. The 4 basic components is the same components in a typical fridge. Okay, it's just that. So this is water to air, means you take groundwater from ground source, and you pump it through the evaporator, and you produce heated or cooled air throughout the ductwork supplied to the space. Now, for example, for heating application, if the heat pump has a COP of 4.0, COP means coefficient of performance. If you have a 4.0 COP, that means for every 4 BTU of heat delivered to the space, you use up 1 BTU of electricity and 3 BTU from the ground. Okay, so you can see it's very efficient. This is also a geothermal heat pump. It's a water-to-water. Now, same components inside the casing. Same configuration here with the ground loop pump. And instead of producing hot air or cool air, you're producing hot or chilled water with a pump it around to fan coil units or whatever air handlers for cooling or heating. The different configurations for geothermal heat pump systems. This picture shows, I don't know why it's not showing up the ground. Well, this in my computer, there's a line here shows the grade level here, and you have the heat pump in the mechanical room. This is the building here, and then you have buried horizontal plastic pipes, the HDPE pipes, high density polyethylene pipe. Okay, you bury it horizontally, usually below 6 feet, and then you fill the ground loop with a glycol water solution, and then you have a pump the water around and pump through the heat pump to take the heat away from the heat pump or take heat from the ground to the heat pump. Okay, so the ground acts like a big heat storage device. In the summer, you reject heat into the ground, and then in the heating season, you extract heat from the ground and gets pumped into the space for heating. Another configuration, vertical closed loop. Now, instead of burying the horizontal, the plastic pipes horizontally, you drill boreholes. Typically, could be 200 feet deep, 400 or 500 feet deep, sometimes even 600 feet deep boreholes. You can have 1, 2, or many of them, depending on the size of the load, your building. Okay. Same configuration here. You have a pump the water around and through the heat pump. Now this is this configuration is called standing column well. It's an open system. Open in the sense that You also drill a borehole, usually 6-inch diameter or 8-inch. Can be very deep, 500 feet deep, 1,000 feet, or even 1,500 feet deep, sometimes 2,000 feet deep, okay? And then as you drill so deep so that you have groundwater in the well, it's a water well. And then you have a submersible well pump here. And then you have a shroud pipe down to the bottom with holes in it. The pump pumps water from the bottom of the well, pump the water through the heat pump here, and the water dumps back at the top of the well. So basically you're utilizing the whole depth of the well as a heat exchanger, okay? It's open. You're using the well water directly to the system. And for this type of system, you already have an emergency bleed. For example, when you're doing heating in the winter, right? You're pumping water from the well, you're extracting heat out of it. So the water gets colder and colder until it reaches an equilibrium point. And that temperature could be very low. If it becomes below freezing point, that's a problem. So you have an emergency bleed here. If the temperature gets too low, you bleed some water out, and then the water is going to make up from the surrounding ground, which is warmer, okay? And same deal for the cooling season. If the water gets too hot, as you are constantly rejecting heat into the well, you bleed some of the hot water here, and the surrounding cool water is going to make up to the well. Another configuration, if you have a large body of water near your building, like a lake or pond, it's very clear here. This is a pond here, a lake. Okay, inside the building, mechanical room, you have a heat pump. This configuration is a closed loop in the sense that you're not taking the lake water to use directly, but you drop down a heat exchanger here. You pump the water in the closed loop through the heat exchanger and back to the heat pump. Another configuration is that you don't use a heat exchanger in the lake, but you take the water from the bottom of the lake and pump it through the heat pump, and then you dump back to the surface of the lake. This system relies on the fact that if the lake is deep enough, in the bottom, the water temperature stays constant throughout the year. So it's warm in the heating season and cool in the cooling season. A map shows the groundwater temperatures across the country. Different states, different locations have different ground temperatures. Like Boston, it's 50 degrees year-round. Philadelphia, 55. Miami, it's hot, 78. Constant ground temperature means warm during heating season and cool during cooling season. Warm and cool compared with outside air temperature, obviously.
Excuse me, at what depth is that?
Well, good question. Now look at this chart here. This chart shows the temperature variation around the average temperature in the ground across the year. Now, this line shows 2 feet below ground. Okay, it changes a lot through the year. 5 feet below the ground, dotted line, changes a lot, somewhat. 10 feet changes a little bit. When you get down to 30 feet, it doesn't change. Okay, so basically that ground temperature means below 20 feet, 25 feet.
Why do geothermal systems or these ground source systems go so deep?
Well, because they're utilizing the boreholes as a heat exchanger. Okay. And the size of the heat exchanger is driven by the depth of the borehole. Okay, you need the heat transfer surface area to do a certain amount of heat transfer.
But if you were to build a deep foundation,
yes,
and you went to that magic 20-foot level,
and
then just went around the building,
yeah,
would that be an efficient system?
Yeah, if you have sufficient land area, because a horizontal system takes a lot of land area.
Right.
okay? And if you don't have ledge, trees, and everything. Now, another reason why the geothermal heat pump system is efficient. Let's say you have a big building, right? And you know, a big building in the interior zones, you never need any heating throughout the year. You always need a cooling, okay? But the perimeter zones, you need the heating during the heating season. So what happens is that when the heat pumps are running, the units that's doing cooling, it rejects heat into the same ground loop, and that heat gets utilized by the heating units. Okay, so the waste heat gets utilized. That's partly why it's so efficient. Now I'm going to talk about some example projects. The projects are from, some are cited from a Geo Outlook magazine, some from the ASHI Journal, American Society of Heating, Refrigeration, and Air Conditioning Engineers, ASHI. You guys know that, sure. And some projects engineered by my own firm. Oops. Okay, you seen this? You saw this map before. The whole country. This is the state of Idaho. You see, they have a lot of high groundwater temperature areas. Brown areas, water temperature above 212 degrees. Blue areas below 212 degrees. So they have a lot of geothermal energy available. So the city of Boise, Idaho, they created a system, geothermal system, with 4 districts. They pump a total of 775 million gallons of geothermal water from underground annually. And they drill the production in the injection wells from 400 feet deep to 3,100 feet deep. Because to get that high temperature water, you have to drill that deep. Okay. Sometimes they get the hot water from 400 feet deep, which is very desirable. Temperature range from 154 degrees to 175. Well, the reason they have production in the injection wells is that you drill a borehole, you take the hot water out, and you use it. And you have to send the water back to the ground because the water is going to get depleted if you don't send it back. And then you have to drill another borehole to send the water back down. And that injection borehole cannot be too close to the production borehole, obviously, because it's going to short cycle. Now the overall system consists of wells and heat exchangers inside the buildings and underground distribution piping, and also the pump centers, like this big pump. It serves 200 homes and 85 government buildings. The system has been running for 28 years. They reported some maintenance issues, like corrosion on the pipes. So they changed the fittings to non-metallic fittings. And for new piping work, they use stainless steel piping. Now, one of the districts is the Boise Veteran Medical Center, then converted to geothermal in 1988. Okay, they have 30 buildings over 60 acres. Anticipated 80 years of payback, but achieved in only 5. Operated for 20 years with no trouble. It's an EPA top-rated energy performer for hospitals in the United States. This is a small inn in Eureka, Colorado. It's located at 10,000 feet elevation in the mountains in Eureka. Eureka is a mining town. Previous mining town is abandoned, but people used to mine, I don't know if it's gold or something. So it's a 28-room lodge, 11,000 square feet, and they used to use a propane tank for heating, but they have a 1,000-gallon tank, but it only lasts a month. You know, in that location, it snows a lot. Once the snow falls, the roads are blocked, so they cannot get more propane. So they have to close the lodge in the winter seasons. So it's a loss of business. So they installed a geothermal system. They utilized the warm water in the abandoned mine shaft. They built a cistern, water cistern tank in the mine shaft, and then pump that water to the heat pumps inside the lodge. So that system has been heating the old building to 70 degrees in the winter, and estimated savings $1,650 per month. Installed in 2008, and the building now operates year-round. This is a project in England, Mansfield, England. It's a hospital, 920-bed modern state-of-the-art hospital, 1.4 million square feet. They utilize the Kings Mill Reservoir lake, and they drop in 7 200-ton Slim Jim heat exchanger in the pond. The lake is across the highway from the hospital, so they utilize the directional boring to run the pipes to pump the ground loop water to the heat pumps in the building. It's supposed to be running this year. Another building, a grain research center in Montreal, Canada. Now, the weather in Montreal, Canada is very hot and humid in the summer and extremely cold in the winter, down to -30 degrees. They have a 25,600 square feet main building, plus 3 1,700 square foot greenhouses. Now, the greenhouses use a lot of energy, and I'm sure you know why. It basically doesn't have an envelope. It does, but very thin and no insulation. So they built a geothermal system, have 24 500 feet deep boreholes, and they use the geothermal system to preheat they had a solar wall, which is a pretty new thing to preheat the fresh air, and also use the geothermal ground loop water to preheat the fresh air too. Now the way they preheat the air with the ground loop water is not through the heat pump. You pump the groundwater from the wells. Let's say you have, I don't know, the groundwater in Montreal must be lower than Boston. Let's say you have 30 degrees, which is pretty low. Considering the outside air is -30 degrees, 30 degrees is still a lot of heat to preheat that outside air, okay? Preheat. And then you use the heat pumps to heat the outside air to the desired temperature. They achieved the 54% energy savings compared with conventional system. $63,000 per year savings. Greenhouse gas emission reduction, so many tons per year. And they received some government incentives as well. Payback time is 4.3 years. It's pretty attractive. This is 2008 Olympics, Chinese National Stadium. They also built a geothermal system. They drilled 104 boreholes in the field, in the track areas. The system is used to heat the media rooms, athletic suites, and underground venues. Now, the whole Olympic village in Beijing, 30% of the village is somehow powered by clean energy, including solar, wind, and geothermal. And geothermal, as part of the clean energy resources, help the Olympic village to obtain the LEED Gold certification. Liberty Island, it's a new project done recently. I think the authority have a jurisdiction is the National Park Services for this place, and the National Park Services did not want to have boreholes drilled in the island, but the managers of the island took them and engineers, architects, took them 10 years to convince them to. They finally agreed, so they built a geothermal system. It's an open loop standing column well system. Then drill 1,550 feet deep, 8-inch borehole, not 6-inch. Well, actually, 8-inch borehole. And because it's an island, they had to use the barge to transport the drill rigs and all the equipment to the island. As you can see, it's only 7,000 square foot facility. The cost is $700,000, $100 per square foot. But maybe it's worth it, considering the location, you know. Otherwise, you would have to build cooling towers, and nobody wants to see that in that location. Energy savings 35%. And also, electricity utility is expensive in that location because it's hard to get to. And now they don't need any fuel oil, just electricity. That's why they did it. A hotel in Spring Hill, in Pensacola Beach, Florida. This is the location, the island. 80,000 square feet hotel in the beachfront. The weather is hot, humid, and salt-laden in Florida. And water and sewer is very expensive. Potable water has to be piped from the mainland. Sewer processing is a challenge, as you can imagine. They have a limited site area, so they only drilled 98 boreholes, which is not enough to take care of the total load of the building. So they built a hybrid geothermal system, which means they also had a fluid cooler. It's similar to a cooling tower. It's just a closed loop. The hybrid system provides space heating and cooling, domestic hot water heating, pool and spa heating, outside air cooling and heating, also ice machines. I'm sure they have a lot. Ice machine cooling throughout the hotel. The hotel opened in 2002. They metered the energy consumption for a year, and they were able to maintain the indoor air temperature at a very comfortable level. They have reported a very low maintenance cost because now you have fewer components exposed to the salty environment. You know, the salty air tends to corrode the metal parts of the equipment. They have consistent system performance and availability, low life cycle cost. Also reduce the water consumption because Florida needs a lot of cooling, so the cooling towers must be running all the time. Now you saving some cooling towers, you save a lot of water usage. Payback time, not even a question. The system costs less than a conventional system. So this is very impressive because you know that geothermal system, because of the drilling, usually costs a lot more upfront, but because of the scale of the building, it's a large building, so the payback time is shorter, and this particular one actually beats the conventional system. Mistry Community Center in North Quebec, Canada. It's a community building, 75,000 square feet, has ice arenas, locker rooms, gym, fitness centers, libraries, fast food, and offices. Now the arena is a very high energy consumption place because you have heating and cooling going on simultaneously. You have to cool the ice arena and also heat the space for comfort. So they built a 28 borehole geothermal system. They use water-to-air heat pumps for space heating and cooling. They also have water-to-water heat pumps to do cooling, to maintain the ice temperature. And the water-to-water heat pumps also used for domestic hot water heating. And one reason why this is so efficient, as my previous slides showed, where you have multiple heat pumps, some does cooling and some does heating, you get the efficiency of diversity. The rejected heat get utilized. They also used the energy recovery wheels, some other energy saving measures. 62% energy savings compared with the model National Energy Code for buildings, this Canada building code. $153,600 annual savings. They got some incentive from the government as well. 4.6 years of payback time for the system. This project is very close by in Dedham, Massachusetts. Also very new project. I don't know which architect did this or engineer, but it's a community center for 2,000 people. They built a geothermal system, closed loop again, 408 boreholes, 1,600 tons of cooling and heating capacity. It's also a hybrid system. I think they came to the hybrid system because for the calculations on the upfront cost, energy efficiency, considering all the factors. That's what they came to, and the cost is $4 million. Estimated energy savings is 20%. Seems low to me. I don't know why. Maybe they could have done a better job. Projected energy cost savings, $325,000. Still very impressive. 7.5 years payback time. Because it's a not-for-profit organization, they don't pay taxes, so they don't get any tax incentives. This is a high school building in Michigan. They built a horizontal ground loop system. They drilled some boreholes, and one feature of this system is that this school, because they don't have fire service water available, so they had to build a pond in case there's a fire. So they make use of the pond. They run some of the ground loops in the water and some loops in the ground. So it's a combination of things. It's a school building, so they have individual heat pumps for every classrooms. So it's very good individual control for the classrooms. And also the fact that every space has its own heating and cooling unit. You save a lot of ductwork. Energy savings is 35%. They achieved the LEED Silver certification. They also utilize the ground loop to cool the water freezers, the condensers. Because of the indoor air quality and the thermal comfort, the teacher and the student attendance went up significantly. So it's a very successful project. Boise State University, Muncie, Indiana. The whole campus have 40 plus buildings, 5.8 million square foot, 80,000 students, and 3,500 employees. They are converting the entire campus to geothermal system. The first phase, they drilled 2 borehole fields. They drilled 1 borehole field now. It's going to have 2 borehole fields, 2 district energy centers with campus distribution piping. They used to have 4 coal-fired boilers. You can imagine the big, dirty chimneys out of that. The chiller and heat pumps in energy centers to produce chill water, 42 degrees and 150 degree hot water for space heating and cooling, and also domestic hot water. $93 million project. First phase, they drilled 1,800 boreholes. Project began in May 2009. They're going to have a total of 4,100 boreholes once the project is finished. Estimated annual savings $2 million, less than 9 years of payback time. Another whole campus conversion project, West Chester University in Pennsylvania. They're converting 1.8 million square foot of building space, including dormitory buildings, classrooms, faculty, office buildings, from steam heating to geothermal heating. The first phase is going to be 170 boreholes drilled under tennis courts. The district geothermal system is going to have common borehole field, central pumping house, individual heating and cooling units installed for each dorm unit. So again, they're going to have very good individual control since every dorm has its own heating and cooling units. Estimated the savings for one of the buildings, 378,000 square feet, 50% for heating and 10% for cooling. Annual savings, $220,000. Another 2.4 million square foot of building space is going to be added to the geothermal system. The total tonnage will be 4,600 tons. Huge system. This project is done recently by my own firm. It's a big house in Rye, New Hampshire, about 15,000 square feet. They had a existing system was a propane-fired boiler system for heating. For air conditioning, they have 6 split systems. Condensing units sits outside. We finished up the project by the end of 2009. We finished on actually 12 o'clock midnight, December 31st, 2009, because we have to start up by that date to get the tax credit for that year. This is a drill rig. It used the down-the-hole hammer, compressed air drilling. Big machine is 40 feet long, roughly, and 8 feet wide. The mast is very tall too, about 40 feet, I think, 40 or 50 feet. We had to do the flow testing, flushing flow testing for the ground loop before we do the backfitting, because you want to make sure there's a lot of heat fusion joints for the plastic pipes. You want to make sure there's no leaks before you bury them. And also you want to make sure the water flows through the U-tubes in the boreholes. There's no restriction, and you get the designed flow rate. So we have to do the flow test. If something's wrong, you have to cut it out and redo it, or even re-drill the boreholes. That would be a disaster. So we did all those, and because it's December and it was snowing, the pipe is all frozen up. So we couldn't do the flow test. So we put some ground heaters, and we heat it up, and then we do the flow test. And then after everything is so fine, we bury it.
What was the length of the ground loop, more or less?
Well, this header pipe from the borehole field to the mechanical room is about 200 to 300 feet.
So you had to heat that whole length, more or less, to get it.
Well, the main header pipes we don't heat. We heat this the borehole areas, borehole field. The main pipes was fine. Actually, yeah, that's the case.
How much did the system cost?
A lot of money.
How much money?
I don't know exact number, but it's $600,000 to $800,000. It's in the pattern because this is a very high-end house. It's like a museum, so everything is expensive, inside, outside. Outside is like a park, you know, it's all those expensive landscaping. You have to redo it. So it's not a typical project. So you know, you don't scale down to a typical house.
But when you other project, you said this much saving.
Yes.
Is it compared to what?
Compared to the older systems.
Older system. Okay.
The propane-fired.
Conventional,
Conventional, yes. Either natural gas or oil-fired systems. This is how it looks like inside the split-type heat pumps in the basement, condensing units, and then the blower units in the attic, ductwork, the pump room, the ground loop pumps. The owner was very happy with this system. It maintained 72 degrees year round. And we installed the electricity meter for this system alone. We metered it, and we did the calculations, and savings is 60% for heating and 40% for cooling. So he's very happy. We also did a snow melting system for the house. A huge driveway with all the nice bricks. 7,500 square feet. He had also the propane tank, used propane fired boiler, 1.4 million BTU boiler to serve the snow, serve the driveways, snow melting. The propane bill for December 2008 alone was $12,800. So we retrofitted the system with a big geothermal system, 62 boreholes. This is really a commercial system. See all those boreholes?
Just for the driveway?
Just for the driveway. Well, I mean, people feel bad about this, but maybe you find some comfort knowing that besides the driveway is a wetland. Okay, if you don't have a snow melting system, you have to put salt. The salt is going to be flushed into the wetland. You know, I mean, you get some benefit there, but maybe a minor point. No, it's something to consider. Okay. Here's how you do the grouting. Remember the vertical boreholes? You plug in the U-tube. You have to grout it. The reason you grout it because you don't want it's a requirement, EPA, DEP requirement. You don't want the surface water run into the borehole, and the different aquifer layers in the ground get cross-contaminated. So you grout the whole thing. And here we do the flow testing for the U-tubes once they are grouted and in the ground. Here's doing the trenching. The head pipes in the trench before it's backfilled. Big heat pumps inside the mechanical room, water-to-water heat pumps. You produce hot water, and then hot water gets pumped through the driveway. This is a big snowstorm this January, 15 inches of snow. It worked.
Guiltless luxury.
Another project we did in Cape Cod, a developer is building 9 houses in a lot. So I designed a centralized geothermal system. So they're going to have an owner association. The association is going to manage the central ground loop and the pumps. And then the individual house owners is going to run their own heat pumps in their house. Then pay their electricity. So they have the incentive to save because they're paying the heat pump. And we use the sonic drilling because it's Cape Cod. It's all sand. It's not rock like the rest of New England. It's all rocks. So you have maybe 20 feet or 40 feet topsoil. Once you pass topsoil, you drill into rock. The borehole, you have no danger of the borehole collapsing. But in Cape Cod, it's all sand. Boreholes with cave in if you. So we use the sonic drilling. It's like a empty pipe, shake down with some drilling fluids. It's very quick, okay, and less expensive too. And obviously the borehole doesn't cave in. You have this steel pipe holding it. We have 26 boreholes arranged in 2 or 3 boreholes each group. You know, have the big drilling rig at one location. You drill a vertical borehole without moving the drill rig, and you turn an angle. You drill another one, and then turn another angle and drill another one. So you drill 3 boreholes in one location without moving the drill rig. So you save a lot of time because it's a big thing to move the huge truck and the drill rig. It's right now in construction. The ground loop is almost done. Now, the reason we designed the system this way, to have a central ground loop system is like I showed you that slides where you have multiple heat pumps. Sometimes not every heat pump is running at a certain time. Now, when not all heat pumps are running, you're not taking so much heat out of the ground during heating season, so the groundwater temperature is warmer. And warmer ground temperature means a higher heat pump efficiency, so it's very efficient. Now we talk about some of the benefits. Sustainability, high energy efficiency, obviously. Cost savings could be as high as 70%. I mentioned that for that housing, right, heating savings is 60%. That was based on $2.16 per gallon of propane. Propane, I think the price went up just recently. And some people are paying $3.50. So if you redo the calculations, it's 75% savings. Another benefit is available continuously throughout the year. Wind, solar are all good things, but it's not available all the time or everywhere. Reduce carbon footprint, reduce water consumption, no cooling towers. Cooling tower water treatment chemicals eliminated. For residential houses, better air quality as well. Not only in terms of temperature and humidity, but also heating oil, smells, flue. Reduce the life cycle cost. You can achieve LEED energy and atmospheric credits. Even though it's not considered for on-site renewable energy for the ground source heat pump systems, but you are good for the EAC 2 points, energy performance of the building. The LEED new construction 2.2 version has a total of 69 points for LEED certification. But LEED 2009, you have a total of 100 points. The EAC 1 points used to be 10, which means 14.5%. Now it's 21%. So that means LEED USGBC is putting more emphasis on energy performance of the buildings for LEED certification. 14.5% increase to 21% emphasis. Tax benefits. For residential houses, you get 30% of the construction cost as tax credit or grant. If the house, if the system costs you $50,000, you get $15,000 from the government, and that includes the construction, engineering fees, everything. It's good until the end of 2016, but I don't know if the money will run out. I mean, if the government runs out of money, then so you want to do it earlier and quickly. For commercial buildings, you get 10% tax credit. Now, for 2011, this year only, you also get to do 100% depreciation for the construction cost of the geothermal system. Not many people know about this. It's not very well publicized.
What does that mean?
Well, if you have a commercial building, you build a geothermal system this year, 2011. Let's say if it costs $1 million. That $1 million, when you do the tax return, it's a total deduction. Because this is your asset. Usually you have 5 years of depreciation, right? The government allows you to do 100% depreciation. It's like a deduction.
Only for this part.
Only for this year. Yeah. Next year, I don't know if they're going to extend this measure. If not, then you have to do the depreciation. But you get the 10% tax credit anyways for all the years through 2016. See, if you do an example, if your project costs $500,000, right? 10% credit, that's $50,000. That's what you get directly. And the remaining cost is 500 minus 50, 450,000. 50% of the credit, 50% of the 50,000, that's 25,000. And then the depreciation amount is $450 plus 25, which is $475,000. That's the amount you deduct from your taxable money, okay? So if you have a 35% tax bracket, that gives you a saving of $166,000 plus the $50,000 you get there. That's the total savings you get. So the project cost is only $500,000. You almost get half free. So that. Yeah. Was also for commercial buildings. And here is the. This is the for EPAC for energy efficiency for buildings. Not only geothermal, all kinds of energy efficiency measures. 3 categories: lighting, HVAC, building. If you do some measures and you reduce energy to certain levels, you have to do energy modeling, the whole building energy modeling. The savings has to reach a certain percentage. And then if you do lighting, you can get up to 60 cents per square foot of credit, of deduction, tax deduction. And HVAC, another 60 cents per square foot. Envelope, another 60 cents. So you can get up to $1.80 per square foot for tax deduction where you do the tax return. Section 179D tax benefits for designers. Now, a lot of government buildings, because they don't pay tax, and that tax benefit gets passed over to the designers, architects, engineers, civil engineers, contractors. Government buildings includes schools, state universities, government office buildings, and hospitals, military bases. This is different scenarios how the designer team share the tax benefits. 1-party engineer, 2-party engineer architect, 3 parties engineer architect, design build contractor, or 4-party. Split them evenly. I think it's very attractive if you get to do such a project. There are also state and local incentives. This website, Desire database for state incentives for renewables and efficiency. You can check them out for your projects. Reduce the maintenance is another benefit. No cooling towers, no moving parts, so you don't have to do the water treatment, winterizing cooling towers, no chillers and boilers, and reduced inside the cooling and the heating equipment. You used to have a boiler. Now you don't have to have a boiler. You don't have the hydraulic system. The same heat pump does both heating and cooling. The ground loop is buried there. It lasts forever. You never need to maintain it. Now, per a study done by ASHI in 2000, maintenance costs for geothermal systems for commercial buildings range from 7.32 cents per year per square foot to 9.36 cents per year per square foot. Conventional HVAC costs 32 cents per year per square foot to maintain. So it's a bigger reduction. Architectural benefits. You don't have to struggle to hide the cooling towers. It also eliminates some potential structural work if the cooling tower is going to be mounted on the roof. No condensing units to hide. Ground loop invisible. No boilers and chillers. Mechanical rooms can be smaller. Also, you have a diversified range of heating and cooling equipment. The heat pumps can be horizontal, can be vertical, can be split type. Very flexible for your space design. And also the multiple utility units, heat pumps. They serve the space. They sit in the space where they serve, so save ductwork and the clearance requirement. And the response to the occupancy and the internal loads better. Another nice thing is the geothermal is very good for radiant and floor systems because the geothermal heat pumps produce hot water in the range of 90 to 120 degrees. That's an ideal temperature range for radiant floors. You know, if the temperature is too high, it may crack the floor. If you have a daycare center, for example, you have kids crawl on the floor all the time, it's very nice to have a radiant floor system. So that's one of the benefits. Some potential issues. Open loop systems. The biggest issues are corrosion. Because you use the water directly from the well, your minerals, sediments, and so you need to use heat exchangers to isolate the ground loop, the well water, and the inside loop. But once you use the heat exchanger, your efficiency goes down because you isolate there's an efficiency loss at the heat exchanger. And because of the sediments, you need a filtration system so that you don't clog the heat exchangers and the condensers. Also, because you are pumping water from the bottom of a deep well to the surface, the pump head is high, and that consumes more pump energy. And a lot of cases, you need the emergency bleed. You need to obtain the permit from a local sewer or stormwater authority, or from EPA if you want to discharge to a surface water body. You need to file an underground UIC, underground injection control registration, and for which you have to do water testing and lab analysis. If you have to drill in a wetland, you have to get the permit from the local conservation commission. You may check out these guidelines for geothermal systems from Mass Department of Environment Protection. They revised it in August last year. For lake systems, one of the issues is that the water body has to be big enough to handle the load. If the lake is not big enough, and during heating season, the water may get too cold and may cause freezing in the heat pumps. Here's an example, a bad example. A house in Cambridge. This is a Longfellow house in Cambridge. I think George Washington once sits in that house to set up an office in that house. So it's a national historic site. They built a standing column well geothermal system in 2000. By 2008, the system is totally dysfunctional. Well water flooding due to imbalance of water flow between the two wells, waterborne sediments, corrosion, pump failure, break of the shroud pump. So in 2005, they have to install a new control system to take care of the water imbalance issue. 2006, they had to install the electric heaters because the compressors failed. 2007, they have to put in the heat exchangers to isolate the well water and the inside the loops, heat pumps. In 2008, the well pump failed, and they used a video camera, and they found out the shroud pipe broken and causing a loss of 75% capacity. Same year, the other pump failed as well.
Do you have any idea why that all?
Corrosion,
Yeah.
sediments, bad design. I don't think they have an engineer on it. I think the equipment vendor did the whole thing. And then they end up hiring one engineer to do a study and another engineer to do another study. And then they're looking for contractors to abandon this system and build a closed loop system. I don't know who got the project. I was there, and our team didn't get it. Another example, a 2,600 square feet house built in 2007 in Connecticut also had a standing column well system. The owner is an architect, so he had problems. He called me, and I went there and took a look. $500 to $600 per month during heating season. Only spend there in the weekends. Weekdays, the thermostat is 55 degrees. So, you know, it's amazing. January 2009, 28 days, the bill was $770. So I went there, took a look, and found out that, you know, they initially hired an engineer, and then the equipment vendor came in and said, you don't need that, you don't need drawings, we'll do it for you. And they came up with their own drawings and just did it their way. Yeah.
Why the electricity is so high?
Huh?
Why is the electricity so high then? Why did you find?
Because they did a great job. It's a bad job. Well, different trades didn't coordinate right because they didn't follow the engineering drawings, okay? And they have HVAC contractor, just a control guy, electrician, and the driller. They just do their own things. It's not well coordinated. And I went there, I took a look, and when it's doing heating, they have a heater in the water tank, electric heater in the tank. That's running all the time. It's bad control. So when the electric heater is running, so the water temperature is always satisfied. It's satisfied by the electric heater. So the geothermal system doesn't need to run.
Was that electric heater added to the project? It wasn't in the original drawing?
That I don't know. I think it's original. Also, the well pump uses a lot of energy. As I said, you have to pump the water from the bottom of the well to the surface. It's not like a closed loop. A closed loop, you know, although you have the same depth of the borehole, but it's a closed loop. You only have to overcome the friction of the pipes. You don't have to overcome the 500 feet of water column in the well.
What's usually the material of the pipes?
Plastic pipes, HDPE, high density polyethylene. It's similar to the pipes that you see in the gas station, the black pipe. It lasts a long time when it's buried. It's resistant to corrosion, minerals, and everything.
How good is the heat exchanger?
How what?
How good is that pipe at exchanging heat?
You know, plastic is not a very good material for heat transfer. And that's why one of the reasons why you need deep boreholes. You need the surface to compensate for that. Comparison, another house, a good example, 1,600 square feet. Then convert the oil-fired system to a geothermal. The monthly bill dropped from $600 to $168, also in Connecticut.
So are closed loop systems preferred, and why would you use an open loop?
I always recommend closed loop systems.
Is it, I mean, it seems, yeah, it seems like.
Yeah, you know, sometimes people are forced to open loop systems, standing column wells, because you don't have the land area to drill more boreholes. You know, the standing column wells, you can drill deeper. Because you use the water directly, you can save a lot of boreholes, okay? So you don't need that big land areas. And sometimes people even drill boreholes inside the building for standing column wells. But I think its use is limited to some areas. Areas where you have very good water quality, okay, like some places in New Hampshire. But a lot of places, if the water is salty, brackish, that's a big issue. It corrodes. Issues with the closed loop systems, available land area, just also setback distance requirement. I mean, setback distance requirement also apply to open loop systems. From water sewer lines, private potable water sources, public water supply wells, contamination sources such as septic fields, oil storage tanks, from surface water bodies, and also from property lines. You have to maintain certain distances from all those things. Another risk is unknown underground conditions. You don't know how much groundwater you're going to run into when you do the drilling. If it's a lot of water, you have to deal with it. The local water and sewer authority may not allow you to discharge the water to their storm or sewer lines. In that case, you have to truck it away, okay? Find a place to dump it. Also, you don't know how much ledge you're going to run into when you do the trenching, you do the header pipes. If there's a lot of ledge, and then you have to do the deledging, and it's very costly. Also, the depth of topsoil. When you do the drilling, for the topsoil portion, you have to put a steel casing so that it doesn't collapse. So if you run into more topsoil, you need more steel casing, which is another cost. Also, when you do the ground loop installation, the driller has to do a good job doing the heat fusion, all the joints and fittings, make sure there's no leaks, and the driller has to do all those flow testing, hydrostatic pressure testing. They have to follow the engineer specifications and good practices.
Are there many subcontractors equipped to do this?
Nowadays,
Ask that about the RIDE
yeah,
New Hampshire project.
right. Nowadays, there's a lot of drillers available. All those well drillers before, they all jump into the geothermal business because that's the only thing available now.
How much geotechnical engineering needs to happen prior to even doing any of this? Like, is that a new cost you have to add to a project that wouldn't have been there before?
Well, that's a good point. People don't typically, unless it's a big commercial project, people don't hire a geotechnical person to do some testing boreholes. Residential projects, you just, what you do is that do some research. There's a website, there's a database, the state MassDEP maintained a database of all the wells drilled, how deep it is, whether it's for irrigation or domestic water or geothermal use, and how deep is the topsoil, at what depth they run into water, and what's the rock composition, all those information. And that's the information source, basically, for small projects. Also, there's a National Geographic, I think it's called National Atlas. There's a website, there's a map. You can do some searches of geographic information, what's underneath.
Does USGS have stuff like that?
Excuse me?
The United States Geological Survey?
Yeah, if you hire a geologist, but again, small project, people don't have the money to do that. Large projects, you hire a geotechnical consultant. They even drill some testing boreholes to find out, where's the ledge and how deep is the topsoil. You have to apply for permit in some cases for wetlands, for water discharge. Coordination between the trades, the control guy, electrician, HVAC guy, plumbing, the driller has to work together. I always recommend people to hire an engineer to do the engineering. It's true, not because I'm an engineer, because I've seen the problems. For a residential house, a geothermal system is a small system, but it's more complicated than the size of the system indicates, okay? You've got a lot of components. You got the drilling, you got the water tanks, sometimes pumps, heat pumps, a lot of things to consider. The biggest drawback is the initial cost. And the reasons, the drill rigs are heavy equipment. You have to mobilize them, drill rig and a support truck, drill rod, all very heavy stuff. Fuel consumption is very high. You're drilling through the rocks. A lot of horsepower involved. It burns a lot of fuel. Unknown underground conditions. When the driller comes in to give you a price, he has to consider all those risks. So that tends to drive up the price, because they have to cover themselves. If you run into a lot of groundwater, you have to do the dewatering, ledge removal, and also sometimes a lot of topsoil. You have to do more steel casing. Larger projects, you have to do the thermal conductivity test. That's an additional cost. Also, the tough work conditions. Cold, too hot, and deal with a lot of mud and snow. It tends to hinder the project progress. More time spent on the project, more cost. Also, you need to do the site preparation, trenching, the backfilling. Sometimes you have to put the landscaping work back. The good news is that more drillers are available throughout New England. More equipment manufacturers, geothermal heat pump manufacturers, HDP pipe manufacturers, fittings and accessories, all those things. We have a larger database for existing wells. This is a website I mentioned. As more people do it, you get more experience, bigger the database. And that tends to reduce the cost. And also the tax credits and the incentives. That's it. Thanks for your time.
Thank you.
If you have questions.